They were drowning inside tanks that were supposed to float. April 28, 1944, Slapton Sands, Devon Coast, England, Exercise Tiger. The water was 48 degrees Fahrenheit, cold enough to kill a man in 20 minutes, even if he could swim. But the men going down weren't swimming. They were trapped inside 30-ton Sherman tanks wrapped in canvas screens, sinking stern first into the English Channel, while diesel fuel leaked into the water around them. Lieutenant Dean Rockwell, commanding a DD tank from the 743rd Tank Battalion, felt his Sherman tilt backward at an impossible angle. Water poured over the canvas flotation screen from behind. The propellers were still turning, still pushing, but the tank was going down. He shouted orders to his crew, "Bail out! Get clear!" The driver, his bow gunner, his gunner, his loader, all scrambling for hatches while seawater flooded the fighting compartment. Some men made it out, some didn't. The canvas screen that was supposed to keep them afloat collapsed inward as the tank sank, trapping men in folds of heavy fabric underwater. Rockwell surfaced, gasping in the cold, watching other tanks around him in various states of sinking or struggle. Some had already gone under. Others were wallowing low in the water, their screens torn or collapsed, crews abandoning vehicles before they became coffins. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This was not supposed to happen. Exercise Tiger was the final full-scale rehearsal for Utah Beach, scheduled for June 6th. Everything had been planned, coordinated, rehearsed. The DD tanks, duplex drive Shermans modified to swim ashore ahead of the infantry, were the critical first wave. They would land before the infantry, suppressing German bunkers and gun positions, giving the foot soldiers a chance to get off the beaches alive. That was the plan. That was what everyone from Eisenhower down to the company commanders believed would happen. But here, in a protected bay on the south coast of England, with calm seas and no enemy fire, the tanks were sinking. Not from German shells, not from mines, from something wrong with the tanks themselves, from some failure in the modification that made them amphibious, from something nobody had noticed in the months of testing and training and preparation. By the time the exercise was called off and rescue operations began, 6 DD tanks had sunk completely. Others had barely made it to shore, their crews shaken and their screens damaged. The official casualty count from Exercise Tiger would eventually reach 749 American servicemen dead, most killed when German E-boats attacked the landing craft convoy, but a significant number drowned in or around the DD tanks that had failed. The subsequent investigation was urgent and classified. D-Day was 5 weeks away. The entire invasion plan for Utah Beach depended on DD tanks swimming ashore in the first wave. If they couldn't survive a calm water exercise in a protected English bay, how would they survive 3 to 4 miles of open channel crossing in potentially rough seas under German artillery fire? Engineers from the 1st Army headquarters, from the Ordnance Department, from the British firms that had developed the DD modification, descended on the 743rd and 741st Tank Battalions. They examined every tank that had been in the water. They interviewed every crew that had survived. They were looking for the failure point, the weak link, the thing that was killing tanks that were supposed to save thousands of lives. What they found was worse than a design flaw. It was a structural failure so fundamental that it called into question whether the entire DD tank concept could work at all. The idea of making tanks swim was not new. Engineers had been trying to solve the problem of getting armor ashore during amphibious operations since the First World War. Tanks that could cross rivers, tanks mounted on pontoons, tanks sealed and waterproof to wade through shallow water, all had been attempted with varying degrees of success. But none had achieved what was needed for a large-scale amphibious invasion. a tank that could be launched from a ship miles offshore, cross open water under its own power, and arrive on the beach ready to fight immediately. The breakthrough came from a Hungarian-born engineer named Nicholas Straussler, working in Britain in 1941. Straussler's concept was elegant in its simplicity. Don't try to make the tank itself watertight. Instead, surround it with a flotation screen, a collapsible fabric barrier that would displace enough water to keep the tank afloat. Mount propellers to the rear, powered by the tank's own engine through a transfer case. The tank would swim like a boat, then drop its screen when it reached the beach, and fight as a normal tank. The British War Office was sceptical, but intrigued. They gave Straussler permission to modify a Valentine tank for testing. The tests at the Brent Reservoir near London were successful. The Valentine, wrapped in its canvas screen and powered by twin propellers, floated and moved through the water at nearly 4 knots. When it reached shore, the crew collapsed the screen in seconds, and the tank was immediately combat-ready. The concept was proven. Now it needed to be scaled up, modified for the Sherman tank that would be the primary American armor in the invasion, and produced in quantities sufficient for D-Day. The designation was DD, duplex drive, referring to the dual capability: drive on land with tracks, drive in water with propellers. The British firm of Vickers Armstrong received the contract to develop the DD modification kit for Sherman tanks. The engineering challenges were substantial. The Sherman weighed 31 to 33 tons depending on variant. To float that mass required a flotation screen nearly 6 feet high surrounding the entire tank, creating an effective hull that displaced enough water to provide positive buoyancy. The screen framework consisted of tubular steel struts attached to the tank hull, with a rubberized canvas screen stretched over this framework and sealed at the bottom. Inflatable rubber tubes inside the screen framework provided rigidity, keeping the screen vertical when inflated. The whole assembly could be collapsed by deflating the tubes and releasing quick-release catches, allowing the screen to fold down around the tank hull in approximately 15 seconds once the tank reached shore. The propellers were mounted on a bracket at the rear of the tank, connected through a power takeoff unit to the main engine. The tank commander controlled propulsion through a simple system: tracks for land movement, propellers for water movement, both controlled from inside the tank. Steering in the water was accomplished by varying the speed of the propellers, essentially using differential thrust the same way a boat uses a rudder. The first American DD Shermans were modified in England, starting in late 1943. Training began immediately. The 741st and 743rd Tank Battalions were designated as DD units and began intensive water training in the Solent, the strait between England's south coast and the Isle of Wight. Tank crews had to learn an entirely new skill set. They were tankers, trained to fight on land, navigate terrain, engage targets with their 75mm guns and machine guns. Now they had to learn to navigate by compass on water, to judge currents and wave height, to keep their tanks pointed into the waves to prevent swamping, to maintain engine temperature and oil pressure while running propellers instead of tracks. The training was exhausting and sometimes frightening, but it worked. Crews became proficient at launching from landing craft tanks, or LCTs, swimming to shore, dropping their screens, and engaging targets. The DD tanks performed well in calm water and moderate chop. Confidence grew among the tankers and among the invasion planners who were counting on these swimming Shermans to provide the crucial first minutes of fire support on Utah and Omaha beaches. By April 1944, the invasion plan was finalized. For Utah Beach, 32 DD tanks from the 741st Tank Battalion would launch from LCTs approximately 3,000 yards offshore. They would swim to the beach in the first wave, arriving at H-hour, 6:30 in the morning on D-Day. Their mission was to suppress German fortifications, particularly the concrete bunkers and gun emplacements that covered the beach approaches. The infantry, landing in Higgins' boats minutes later, would advance under the covering fire of these tanks already on shore. For Omaha Beach, the plan was even more ambitious. 64 DD tanks from 2 companies of the 741st Tank Battalion would launch from 5,000 yards offshore in rough seas. They would arrive ahead of the infantry and engage the heavily fortified German positions on the bluffs overlooking the beach. The entire Omaha assault plan depended on these tanks reaching shore before the infantry, because Omaha's defenders were far stronger than intelligence estimates suggested, and the infantry would be slaughtered if they hit the beach without armor support. The numbers behind the plan were coldly calculated. Intelligence estimated that German defenders on Omaha Beach could deliver approximately 3,500 rounds per minute of machine gun fire across the beach during the first minutes of the assault. Artillery observers on the bluffs could direct fire from multiple gun batteries. The beach had almost no cover, just 400 yards of open sand and shingle between the waterline and the first protective terrain. Without suppressing fire from tanks, casualty estimates for the first hour on Omaha ranged from 25 to 40% of the assault force. That meant 3,000 to 5,000 men killed or wounded in the first 60 minutes. If the DD tanks could get ashore and begin engaging bunkers and gun positions before the infantry landed, those casualty estimates would drop dramatically, perhaps to 5 or 10%, saving 2,000 to 3,000 men in the first hour alone. The DD tanks represented more than innovative engineering. They represented the difference between success and catastrophic failure at Omaha Beach. They represented thousands of lives. They represented the possibility that the entire invasion could be stopped at the waterline if the armor didn't get ashore to suppress German fire. Every senior officer involved in planning D-Day understood this. General Omar Bradley, commanding 1st Army, had personally observed DD tank training and approved their use. General Dwight Eisenhower had seen demonstrations and understood the capability they provided. British commanders, whose forces would also use DD tanks at Gold, Juno, and Sword beaches, had incorporated them into their assault plans. The tanks had been tested, the crews had been trained. The concept had been proven in dozens of exercises. Everything was ready. And then Exercise Tiger revealed that something was fundamentally wrong, something that made the tanks sink, something that killed crews in calm water before they ever faced the enemy, something that, if not fixed immediately, would turn D-Day into a massacre. The engineers found the failure point within 48 hours of Exercise Tiger. It was not the canvas screen, it was not the flotation tubes, it was not the propeller mounting or the power takeoff system. It was the welds that attached the screen framework to the tank hull. Major William Duncan, an ordnance officer from 1st Army Headquarters, led the investigation team. Duncan had been a structural engineer in civilian life, working on bridge construction in Pennsylvania before the war. He understood stress loads, metal fatigue, and weld integrity. He examined 5 of the tanks that had nearly sunk during Tiger, tanks that had been pulled from the water before going completely under. What he found made him physically ill. The welds attaching the tubular steel framework to the hull were failing, not from impact, not from battle damage, from the simple stress of waves pushing against the flotation screen. The screen, when inflated and filled with air, acted like a sail. Every wave that hit the tank pushed against that canvas surface. That force transferred through the framework to the attachment points on the hull, and the welds at those attachment points were cracking. Duncan documented the failure mode carefully. The welds were standard arc welds, applied during the DD modification process at depots in England. They appeared adequate for static loads. But waves created dynamic loads, repetitive stress cycles that flexed the framework mounting points. After 20 to 30 minutes in moderate seas, microcracks developed in the welds. After 40 to 50 minutes, those cracks propagated. After an hour, the welds failed completely. When a weld failed, the framework shifted. The screen lost its rigid structure. Canvas that had been held taut by the framework suddenly had slack. Water pressure pushed the canvas inward. The tank's buoyancy decreased. It sat lower in the water. More waves came over the top of the screen. The weight of water inside the screen accelerated the sinking. From first weld failure to complete sinking could be as little as 3 to 5 minutes. The DD tanks that had gone down during Exercise Tiger had been in the water approximately 55 minutes when they began sinking. The timeline matched Duncan's analysis perfectly. The welds had failed after an hour of wave stress. Duncan's report to 1st Army Headquarters on April 30th was devastating in its implications. Every DD tank modified in England had the same weld specifications. Every tank scheduled to swim on D-Day had welds that would fail after approximately 1 hour of moderate wave action. The crossing from launch point to beach at Utah was estimated at 40 to 60 minutes, depending on sea conditions. The crossing at Omaha was estimated at 75 to 90 minutes. The tanks would sink before reaching shore. The numbers were unambiguous. At Utah Beach, 32 DD tanks, launching 3,000 yards offshore in the first wave, would likely lose 10 to 15 tanks to weld failure before reaching the beach. At Omaha Beach, 64 tanks launching 5,000 yards offshore would lose 40 to 50 tanks to structural failure, leaving perhaps 15 to 20 tanks to support the entire assault. And that was in moderate seas. If D-Day brought rough weather, if wave height exceeded 3 feet, the failure rate would be higher. It was conceivable that every single DD tank launching at Omaha would sink before reaching shore, leaving 8 assault companies of infantry to hit the beach with no armour support whatsoever against the strongest German defences in Normandy. The casualty projections were recalculated immediately. Without DD tanks, 1st Army planners estimated Omaha Beach casualties in the first hour would reach 35 to 45%. That meant 4,000 to 5,000 men killed or wounded in 60 minutes. For the entire first day, casualties could exceed 10,000. The invasion might fail completely at Omaha, leaving a gap in the Allied line that German reserves could exploit. General Bradley was informed on May 1st. His response was immediate and unequivocal. Fix it. Fix every tank. Find the engineers who can solve this problem and give them whatever they need. The invasion is in 5 weeks. We cannot delay D-Day. We cannot change the plan. Fix the tanks. 1st Army contacted the Ordnance Department. The Ordnance Department contacted the British firms that had developed the DD modification. Everyone understood the urgency. Everyone understood what was at stake. And everyone understood that they had approximately 35 days to re-engineer and re-weld attachment points on more than 100 tanks scattered across southern England, while maintaining operational security and continuing invasion preparations. The solution, when it came, was almost absurdly simple. But implementing it would require engineering precision, manufacturing speed, and logistical coordination on a scale that seemed impossible given the timeline. The engineer who solved it was a 32-year-old British welding specialist named Thomas Kilvert, working for Vickers Armstrong. Kilvert had spent 15 years in shipbuilding before the war, welding pressure hulls for submarines at the Barrow-in-Furness shipyard. He understood dynamic stress loads on welded joints in maritime environments better than almost anyone in Britain. Kilvert examined Duncan's failure analysis and immediately recognized the problem. The original welds attached the framework directly to the tank hull in single-point connections. Every bit of stress from wave impact concentrated at those individual weld points. The welds were failing because they were being asked to absorb forces they were never designed to handle. The solution was not stronger welds. Stronger welds would still fail, just slightly later. The solution was to distribute the stress. Instead of single-point attachments, Kilvert designed reinforcing brackets that spread the load across a larger area of the hull. The brackets were steel plates, roughly 3 inches wide and 8 inches long, that would be welded to the hull first. Then the framework would be welded to these brackets rather than directly to the hull. The critical welds, the ones attaching the brackets to the hull, would be continuous beads approximately 3 inches long, running the full length of the bracket. These welds would be substantially thicker than the original attachment welds, with multiple passes to ensure penetration and strength. The secondary welds, attaching the framework to the brackets, would also be reinforced. The entire modification added approximately 40 pounds to each tank, negligible compared to the 33-ton total weight. But the stress distribution was fundamentally different. Wave forces that had concentrated at single points now spread across the reinforcing brackets and into the hull structure itself. The welds would no longer be the failure point. Kilvert calculated that the reinforced attachment points could withstand dynamic wave loads at least 5 times greater than the original design. A tank that would have lasted 1 hour with the original welds could now survive 5 hours or more in moderate seas. The crossing to Omaha Beach, even in rough conditions, would be survivable. The proposal reached First Army Headquarters on May 3rd. Duncan reviewed the engineering calculations and approved them immediately. Bradley authorized implementation. The order went out to every DD tank unit. All tanks would be recalled to modification depots for immediate retrofit. Welding teams would work around the clock. The target completion date was May 25th, giving 10 days of margin before the planned June 5th invasion date. The logistics were staggering. 116 DD tanks needed modification. Each tank required 16 reinforcing brackets, 8 on each side where the main framework attached. That meant 1,856 brackets had to be fabricated, fitted, and welded. Each bracket required approximately 20 minutes of welding time for proper penetration and strength. The math was brutal. 620 hours of welding work, plus fabrication time, plus transportation time, moving tanks to depots and back to units. Vickers Armstrong mobilized every qualified welder they had. The Ordnance Department sent additional welding teams from other units. British shipyards contributed welders with maritime experience. At peak, 42 welders were working across 3 modification sites, running 2 12-hour shifts per day. The work was exhausting and exacting. Each bracket had to be positioned precisely to align with the framework mounting points. The hull had to be cleaned and prepped for welding. The welds themselves required multiple passes, each pass inspected before the next, each inspection documented. There was no room for error. A failed weld on D-Day would mean a sinking tank and a drowned crew. Tank crews watched the modification work with mixed emotions. They were relieved that the problem had been identified and fixed. They were disturbed that they had been training for months in tanks that would have killed them. They wondered what other problems might exist that nobody had discovered yet. But they had no choice except to trust the engineers, trust the welds, and prepare for the mission. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The modification work proceeded on schedule through May. By May 20th, 94 tanks had been completed. By May 25th, all 116 tanks were done. Each tank was tested in the Solent, swimming for 90 minutes in moderate seas to verify the welds held. Every tank passed. The structural failures that had killed Exercise Tiger were solved. But there was no time for celebration. The invasion had been postponed 24 hours due to weather, moving D-Day from June 5th to June 6th. That gave tank crews 1 extra day to prepare, 1 extra day to contemplate what was coming, 1 extra day to wonder if the 3-inch welds that were supposed to save their lives would actually hold when it mattered most. June 6th, 1944. 0400 hours. The English Channel, 5 miles south of Utah Beach. LCT 544, carrying 4 DD tanks from Company B, 741st Tank Battalion, pitched heavily in 4-foot seas. Wind was blowing 15 to 20 knots from the northwest. Visibility was poor, just breaking dawn with low clouds and occasional rain squalls. Lieutenant Dean Rockwell, the same officer who had nearly drowned during Exercise Tiger, commanded the lead tank. He had survived Tiger. He had watched his tank's welds fail and felt the Sherman going down beneath him. He had lost men from his crew. Now, 39 days later, he was preparing to launch again, this time into rougher seas, under enemy fire, with the entire invasion depending on tanks like his getting to the beach. The LCT ramp dropped at 05:30 hours. Rockwell's tank rolled forward, diesel engine roaring, tracks clanking on the steel deck of the landing craft. The flotation screen was already erected and inflated. The tank looked absurd, a squat 33-ton Sherman wrapped in a canvas bathtub that rose 6 feet above the hull. But absurd or not, it had to work. The tank drove off the ramp and into the water. The screen held. The tank floated. Rockwell felt the familiar sensation of water taking the weight, the tank riding high, waves slapping against the canvas. He engaged the propeller drive. The tank began moving forward at approximately 4 knots, steering toward the beach by compass bearing. Behind him, 3 more tanks from his LCT launched successfully. To the left and right, other LCTs were launching their DD tanks. Rockwell could see perhaps 8 or 10 tanks in the water around him, all heading toward the beach. The formation was ragged, spread out by waves and current, but they were moving. The critical question was whether the welds would hold. The seas were rougher than during Exercise Tiger. Waves were hitting the screen at irregular intervals, some 4 feet high, pushing the tanks sideways. Rockwell felt his Sherman pitch and roll. Water slopped over the top of the screen occasionally, draining out through scuppers at the bottom. The framework creaked under the stress, but the welds held. 20 minutes into the crossing, Rockwell checked his position. The beach was approximately 2,000 yards ahead, visible through the dawn light. German artillery was beginning to fire, bracketing the landing craft behind them but not yet ranging on the swimming tanks. He estimated another 25 minutes to reach shore. 30 minutes into the crossing, one of the tanks behind him began having trouble. Rockwell saw it through his commander's periscope, wallowing lower in the water than it should. The screen partially collapsed on one side. The crew was trying to keep it moving, but it was clearly in distress. Then it stopped, sitting dead in the water, engines still running but no forward movement. The crew began bailing out, inflating life preservers, abandoning the tank before it sank. Rockwell watched them go down. The tank slipped below the surface, stern first, just like the tanks at Exercise Tiger. But this time, the crew got clear. They were swimming, visible in their orange life preservers, waiting for rescue craft. 1 tank lost, 7 men in the water. But the loss was not from weld failure. The screen had been hit by something, possibly debris floating in the water, possibly a piece of shrapnel from German artillery that was now finding the range. The other tanks kept moving. Rockwell's Sherman pushed through the waves, propellers churning, diesel engine maintaining steady revolutions per minute. 40 minutes into the crossing, he could see the beach clearly. The tide was low, exposing German obstacles, steel hedgehogs, and Belgian gates designed to rip the bottoms out of landing craft. But DD tanks drew less than 3 feet of water in their flotation screens. They could navigate through obstacles that would stop boats. At 48 minutes, Rockwell felt the tracks touch bottom. The tank was in shallow water, less than 5 feet deep. He ordered the screen dropped. His crew released the quick-release catches. The flotation tubes deflated. The canvas screen collapsed around the hull. The Sherman, suddenly transformed from swimming vehicle to fighting tank, drove forward onto the beach under track power. German machine gun fire began immediately, rounds ricocheting off the hull armor. Rockwell traversed the turret toward the nearest bunker, a concrete emplacement approximately 300 yards up the beach. His gunner acquired the target. The 75mm gun fired. The high-explosive round impacted near the bunker's firing port. They fired again, and again. The bunker stopped shooting. Behind Rockwell, more DD tanks were coming ashore. He counted them through his periscope. 2 tanks landing to his right, 3 more to his left. Another 2, further down the beach. 8 tanks ashore in the first wave. Not the 32 that were supposed to launch, but enough to provide fire support. Enough to suppress some of the German positions. Enough to give the infantry a chance. At Utah Beach that morning, 28 of 32 DD tanks reached shore successfully. 4 were lost to various causes during the crossing. 2 swamped in rough seas when waves exceeded their screen height. 1 struck floating debris that tore the screen. 1 suffered mechanical failure unrelated to the DD modification. But the welds held. The reinforcing brackets held. The structural failures that had plagued Exercise Tiger did not recur. At Omaha Beach, the story was different and far more costly. The plan had called for 64 DD tanks to launch from approximately 5,000 yards offshore. But when the LCT commanders saw the sea conditions at 0500 hours, they faced an impossible decision. Waves were running 5 to 6 feet, higher than at Utah Beach. Wind was gusting to 25 knots. Visibility was poor, with rain squalls moving through the area. Some LCT commanders made the decision to launch as ordered. Company B of the 741st Tank Battalion launched 29 DD tanks from approximately 4,000 yards offshore. Within minutes, it became clear this was a catastrophic mistake. The seas were too rough. Waves broke over the flotation screens constantly. Water accumulated inside the screens faster than the scuppers could drain it. Tanks sat progressively lower in the water as their buoyancy decreased. The crews fought to keep their tanks afloat. Commanders stood in their turrets, trying to steer into the waves. Drivers maintained engine power, keeping the propellers turning. But the mathematics of buoyancy and wave action were unforgiving. A Sherman tank wrapped in a flotation screen displaced just enough water to stay afloat in calm conditions with minimal margin. In 6-foot seas, with water constantly breaking over the screen, that margin disappeared. 27 of the 29 DD tanks launched offshore at Omaha Beach sank before reaching shore. Some went down within 5 minutes of launching. Others struggled for 20 or 30 minutes before succumbing. Crews abandoned their tanks, swimming in the cold water, waiting for rescue vessels that were themselves under German artillery fire. Some crews drowned. Others were rescued but spent hours in the water suffering from hypothermia. Only 2 DD tanks from the offshore launch reached Omaha Beach. 2 tanks out of 29. It was the disaster that Exercise Tiger had predicted, the nightmare scenario that the Weld modifications were supposed to prevent. But the welds were not the problem at Omaha. The problem was the decision to launch in conditions that exceeded the DD tank's operational capabilities. The other DD tank company at Omaha, Company A, had a different experience. Their LCT commanders, seeing the conditions, made the decision to bring the landing craft all the way to the beach before launching the tanks. This violated the plan. It meant the tanks would not arrive ahead of the infantry, but it meant the tanks would arrive at all. These tanks launched from approximately 300 yards offshore, in shallow water where the wave height was reduced by the shelving beach. All of these tanks made it ashore successfully. They provided critical fire support during the chaotic first hours at Omaha, engaging bunkers and gun positions, suppressing German fire at close range. But they arrived after the infantry had already landed, after the slaughter on the beach had already begun. The first wave of infantry at Omaha Beach hit the shore at 06:30 hours with almost no armor support. The German defenders, elements of the 352nd Infantry Division, a veteran unit that intelligence had not known was in the area, delivered devastating fire. Machine gun positions on the bluffs had overlapping fields of fire across the entire beach. Artillery observers directed fire from multiple batteries. Mortars dropped rounds into the surf zone where men were wading ashore. The casualty rate in the first hour was approximately 40% in some companies. Company A of the 116th Infantry Regiment lost 96% of its effective strength in the first 30 minutes. Men were pinned down behind beach obstacles, behind disabled vehicles, in shell holes barely deep enough to provide cover. Medical corpsmen trying to reach wounded men were shot down. Officers trying to organize assaults were killed before they could give orders. The absence of DD tanks in the first wave made the difference between a difficult landing and a catastrophic one. The tanks that did arrive, the ones that launched close to shore, helped turn the battle. But by then, hundreds of men were already dead or wounded on the beach. The absence of those 27 sunken DD tanks represented not just lost equipment but lost lives. Men who died because the covering fire they needed was sitting on the bottom of the English Channel. After-action reports compiled in the weeks following D-Day analyzed what happened at Omaha. The decision to launch DD tanks in rough seas was identified as a critical error. The tanks themselves, with their reinforced welds, had performed as designed. The structural failures from Exercise Tiger did not recur, but the operational limitations of the DD concept were now brutally clear. The tanks could not survive in seas exceeding 4 feet. They required relatively calm conditions to make long-distance crossings. They were not the miracle solution to amphibious assault that planners had hoped. For the engineers who had worked through May to fix the weld problem, Omaha Beach was a complex legacy. They had solved the structural failure. The welds held. At Utah Beach, that solution saved tanks and lives. At Omaha Beach, the solution was irrelevant because the tactical decision to launch in rough seas overwhelmed the engineering fix. Thomas Kilvert, the welding specialist who designed the reinforcing brackets, learned about Omaha Beach several days after D-Day, when casualty reports began filtering back to England. He understood immediately what had happened. His modification had addressed one failure mode, the weld stress from moderate wave action. It had not addressed the fundamental limitation of the DD concept. A 33-ton tank wrapped in canvas could not survive heavy seas regardless of how good the welds were. Kilvert's report to Vickers Armstrong, written in June 1944, was remarkably prescient. He noted that the DD tank was a compromise solution, adequate for certain conditions but not a universal answer to amphibious assault. He recommended that future amphibious operations should land tanks from LCTs in shallow water rather than launching them from long distances offshore. He noted that the success at Utah Beach, where seas were calmer and the crossing distance shorter, versus the disaster at Omaha Beach, where seas were rougher and the crossing distance longer, demonstrated the operational limits of the concept. His recommendations were largely adopted for subsequent operations. During the landings in southern France in August 1944, DD tanks were launched from much closer to shore, typically less than 1,000 yards, reducing the crossing time and the exposure to rough seas. During the Rhine River crossings in March 1945, DD tanks were used successfully in river crossings where the water was calm and the distances were short. But Kilvert never forgot Omaha Beach. In interviews conducted after the war, he spoke about the weight of responsibility that came with engineering decisions in wartime. He had designed a modification that worked exactly as intended, but he had also known, even as he designed it, that the DD tank had fundamental limitations that no Weld modification could overcome. He had reported those limitations up the chain of command, and the decision to launch at Omaha in rough seas had been made anyway. For the tank crews who survived Exercise Tiger and went on to fight on D-Day, the experience created a permanent awareness of how thin the margin was between survival and death. Lieutenant Dean Rockwell, who commanded a DD tank at Utah Beach, later wrote about the psychological impact of knowing that his tank had nearly killed him during training, was modified with untested welds, and then performed flawlessly during the actual invasion. He described it as living with constant awareness that engineering decisions made by people he never met directly determined whether he lived or died. The crews who lost their tanks at Omaha Beach, the ones who swam in the cold water while their Shermans sank beneath them, had a different perspective. They felt betrayed by a plan that had asked them to do something impossible. They had been told the DD tanks could handle the crossing. They had been shown the modifications that made the tanks safer. They had launched because they trusted the engineering and the planning, and they had nearly drowned because the plan exceeded what the equipment could actually accomplish. The investigation into the Omaha Beach DD tank losses concluded that the decision to launch in rough seas was a tactical error, not an equipment failure. The LCT commanders who had brought their landing craft close to shore before launching tanks were commended for making the correct decision under difficult circumstances. The commanders who had followed the original plan and launched from long range were not blamed because they had followed orders, but the orders themselves were identified as flawed. The broader lesson, the one that military planners took into subsequent operations, was that technological solutions to tactical problems have limits. The DD tank was an ingenious solution to the problem of getting armor ashore quickly, but it was not a perfect solution. It required specific conditions to work. When those conditions were not met, the technology failed regardless of how well it was engineered. The 3-inch welds that Thomas Kilvert designed in early May 1944 represented a specific, targeted fix to a specific, identified problem. They worked. They saved tanks at Utah Beach, but they could not save tanks at Omaha Beach because Omaha Beach exceeded the operational envelope of the entire DD concept. Engineering could solve structural problems. Engineering could not overcome the fundamental physics of keeping a 33-ton tank afloat in 6-foot seas using a canvas screen. The final accounting of DD tank operations on D-Day showed the complete picture. At Utah Beach, 32 tanks launched, 28 reached shore, 4 lost to various causes, 0 lost to weld failure. At Omaha Beach, 32 tanks launched offshore, 2 reached shore, 27 lost to rough seas, 3 lost to other causes, 0 lost to weld failure. At Gold, Juno, and Sword beaches, where British and Canadian forces landed, DD tanks were generally successful, with most launching from relatively close to shore in calmer waters. The modification work done in May 1944 had accomplished exactly what it was designed to do. The structural failures that had plagued Exercise Tiger were eliminated. The welds held under stress. The attachment points distributed loads properly. From a pure engineering standpoint, the fix was successful. But engineering success does not always translate to operational success, and operational success does not always translate to strategic impact. At Utah Beach, the DD tanks provided exactly the capability they were designed to provide. They arrived ahead of the infantry, suppressed German positions, reduced casualties in the first wave. The landing at Utah was the most successful of all the D-Day beaches, with casualties far below predictions. The DD tanks contributed to that success. The men who designed the tanks, modified them, trained the crews, and made the tactical decisions to launch them in appropriate conditions could look at Utah Beach and see vindication. At Omaha Beach, the absence of DD tanks in the first wave contributed to the chaotic, costly landing that nearly failed. But even here, the lesson was not that the technology failed. The lesson was that technology has operational limits, and exceeding those limits leads to failure regardless of engineering quality. The tanks that launched close to shore worked perfectly. The tanks that launched in rough seas from long range sank, not because the welds failed, but because no weld modification could overcome the basic physics of the situation. The human cost of these engineering and operational decisions was measured in specific, countable lives. The men who drowned at Omaha Beach when their DD tanks sank, the infantrymen who died on Omaha Beach because the armor support they needed was underwater, the crews at Utah Beach who reached shore safely because the welds held and the seas were manageable, the infantry at Utah Beach who survived because tanks were already on the beach suppressing German fire when they landed. The story of the 3-inch welds connects to the larger story of World War II in a specific way. It demonstrates that industrial warfare between modern nations depends not just on production capacity or strategic vision, but on engineering precision at every level. A weld that fails means a tank that sinks, means a crew that drowns, means infantry that dies without support, means a landing that might fail, means an invasion that could collapse. The margin between success and failure in amphibious assault was measured in inches. 3 inches of reinforced weld that distributed stress properly. 6 feet of flotation screen that had to stay intact under wave action. 4 feet of wave height that represented the operational limit of the system. These specific, measurable, physical constraints determined outcomes that affected thousands of lives. Thomas Kilvert's modification, designed and implemented in 3 weeks under enormous pressure, worked exactly as intended. It solved the problem it was designed to solve. It did not solve every problem, because no single fix could. But it was enough. At Utah Beach, it was enough to get the tanks ashore. And that was what engineering in wartime required. Solutions that were good enough, fast enough, to save the lives that could be saved. The DD tanks were retired after the war. The concept was never used again in combat. Modern amphibious assault relies on different technologies: air cushion landing craft, helicopter-borne armor, purpose-built amphibious assault vehicles. But the DD tank represents a moment in military history when engineers created a solution to a specific problem under specific constraints, when that solution worked within its operational limits, and when the difference between working and failing was measured in the quality of welds that most people never saw. For the men who swam to Utah Beach in DD tanks on June 6, 1944, the 3-inch welds were the difference between reaching the beach as a fighting crew and swimming in the English Channel waiting for rescue. They never saw those welds. They never knew the name of the engineer who designed them. But they were alive because someone had identified a problem, designed a solution, and implemented it with the precision that wartime engineering required. That is the legacy of Thomas Kilvert's work in May 1944. Not fame, not recognition, not dramatic vindication. Just tanks that reached the beach when they needed to, with crews who survived to fight, at a place where the welds held under stress and the engineering worked exactly as designed. In amphibious warfare, that was enough. In industrial warfare between modern nations, that was victory measured in welded steel and human lives saved by engineering decisions made in workshops far from the battlefield. The story began with men drowning inside tanks that were supposed to float. It ended with men reaching shore alive because someone fixed the problem. The story of World War II contains thousands of such moments. Engineering problems identified and solved, tactical errors recognized and corrected, human costs calculated and reduced. This was one moment. 3 inches of welded steel. 35 days from failure to fix. 28 tanks reaching Utah Beach. And the knowledge that precision in engineering, even under desperate time pressure, could mean the difference between catastrophe and success. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.